This presentation on binary choice models discusses regression models where the response variable y is a binary variable in that y takes on the value 1 if the success criterion is met, 0 otherwise. Now, as I note here, binary choice models also go by the name qualitative response models, and I show some examples right here, such as the decision as to whether or not to buy a home. Here, y would take on the value of 1 if a particular family decides to buy a home, 0 otherwise. And some of the explanatory variables that may play into this type of decision making may include household income, mortgage interest rates, and family size. Now, additional examples of cases where y is a qualitative variable would be the decision to go to graduate school or not, the decision as to whether a firm should pay dividends or not, whether a firm should hire more workers as it expands, whether a firm should launch a new product. So in all of these cases, y is a binary variable and would take on the value 1 if the success criterion, as in each of these cases, has been met. Now, there are two types of binary choice models discussed in this presentation, and they are the linear probability model and the logistic regression model, also called the Logit model. Now, the linear probability model, as the name implies, is a case where y, the binary variable, is expressed as a linear function of various explanatory variables. Now, to understand a little better why this type of linear regression model is also a probability model, consider this two variable model, this simple linear regression model. Now, as you know, the deterministic components of the model, which is also the systematic part of the model, is this. So these first two terms right here. Right, so this is the expected value of y given a value of x. That's what this is. Now, secondly, note also that y, by its nature here, is a discrete variable because it takes on the specific values of 0 and 1. And therefore, we can use the expected value definition for a discrete random variable, which is a weighted average of the outcomes, where each possible outcome is weighted by its corresponding probability, as I show here. So what this means is if P2 is the probability of success, which is the probability that y takes on the value of 1, then it means that P1 would be the probability of failure, which is where y takes on the value of 0. So 0 times P1 is 0, and 1 times P2 is P2. With that, you see that the expected value of y is equal to the probability of success P2, which is the probability that y takes on the value of 1. And so, since the expected value of 1 is equal to the probability of success, again, the probability that y takes on the value 1, it means that P2 is equal to the deterministic component of the regression model, which is the same thing as the expected value of y, as I show up here. And you could even express this regression model right up here to be equal to P2 plus the error term, since P2 is equal to this term. So as you can see, therefore, with this expression, P2 is a linear function of the explanatory variables. And in a two-variable model, the predicted probability would be so calculated. It would be the intercept term plus b1 multiplied by whatever value of x that you are including in your forecast. So let's look at a quick example, and you can read this up later or now, but it's about loan approval, the factors that play into loan approval. And this is a quick summary of the regression model. It's a multiple regression model where the likelihood of a loan being approved is a function of down payment, which is how much you put down as a percent of the home value, and X2, the income to loan ratio. So here Y would take the value of 1 if the lending institution grants the loan, 0 otherwise. So for this first customer, the loan was granted. This customer right here has had a down payment of 16.35% with an income to loan ratio of 49.94%. This customer did not get a loan. His or her income down payment was 29.92. However, income to loan ratio is at 27.05%. Anyhow, when you run that regression, you have this output right here. And as you can see, the regression model is statistically significant. About 50% of the variation in the loan approval process is accounted for by the regression on down payments and income to loan ratio. Now we can also see that the likelihood that a loan would be approved is indeed a positive function of down payment and income to loan ratio because these coefficients are positive. Specifically, B1 is 0.0188, meaning that a 1% increase in down payment would increase the approval probability by about 0.0188. In other words, there's a 1.88% chance that a loan will be approved for a 1% rise in the down payments. In the same vein, we find here that B2 is equal to 0.0258, suggesting that a 1% increase in the customer's income to loan ratio raises the approval probability by about 0.0258, so that there is a 2.58% chance of the loan being approved with a 1% rise in the income to loan ratio. And these are all statistically significant at the 5% level. So with that, we can actually go ahead and estimate the regression equation in the way that I have summarized right here. So this is our p hat, the estimated probability, which is the same thing as y hat, the estimated regression equation. So for example, say x1 is 20%, which is our which is the down payment percentage, and this customer's income is $60,000 and the customer seeks a loan of $200,000. So as you can see, the income to loan ratio comes out to be 30%, which is x2. So plugging and playing, we find that the predicted approval probability comes to 0.282. Note also that if x1 increases to 30% from 20%, with the income to loan ratio remaining the same at 30%, the predicted likelihood of the loan being granted rises from 0.282 to 0.47, an increase of 0.188 in terms of the probability. So a 10% increase in x1 in the down payment raises the likelihood that the loan will be approved by 0.188. Now though, unfortunately, there's a couple of problems associated with the linear probability model, which as you can see is quite, I should say, linear, no pun intended, in implementing, since it's based on the ordinary least squares approach. But the problems include: one, the models can produce predicted probabilities that are either greater than 1 or less than 0, and in which case it would have no economic interpretation, since probability should be bounded within the closed interval of 0 and 1. For example, you will find that the predicted probability would take on a negative value of 0.0932 if x1 is 0. In other words, if the customer has no down payment, however, with income to loan ratio of 30%. So this outcome here makes no sense. As well, the outcome that p hat is more than 1, in this case 1.0372, with a 60% down payment and income to loan ratio of 30%, equally does not make sense. So I demonstrate those issues here on spreadsheet actually, if I may show it to you right here. So you can see what I did here. I changed the down payments by 10% from 0% to 90%, leaving X2 to be the income to loan ratio to remain at 30%. And then right here you can see the calculation up here. I recalculated P hat. And as you can see, quite surely, as down payments percentage increases, we see that the probability of success, as it were, also increases. But find, you can see here that in some cases, P hat is negative, and in a few other cases, as you see down here, P hat is more than 1. So these are empirical, or actually statistical problems that cause this estimation process to be a little bit wanting in terms of its ability to help us predict outcomes. The second problem that's mentioned in the handout is that the changes in probability from one level to the next level is the same across the board. For example, if a customer initially says, I'm going to put down 10%, and then subsequently says, okay, I'm going to kick it up to 20%, surely we would expect the probability to increase as it has. And in this case, it goes up by 0.1884. Now that's fine, but think about this. If another customer says, I'm going to put down 70% and then subsequently changes his or her mind to 80%. Again, sure, we would expect the likelihood of loan approval to increase, but for goodness sake, as you can see here, it really shouldn't be by the same rate of increase as we would expect a customer moving from 10 to 20. Now, when you're putting down a 10% down, that's below the threshold of 20%, because below 20% you're going to pay personal mortgage insurance, and that's not going to be viewed as very conventional when your down payment is less than 20%. So with you kicking it up to 20%, yeah, I would expect the bank to be quite enamored to significantly view you as a good prospect. Now, with 70% down, you already are a very good prospect. So if you change your mind to 80%, how wonderful a customer you are, while that has increased, it really is not saying anything much more than what you already were, a very good individual who can put down 70% to take out a mortgage loan. So I guess the point to note here is that we would expect the increase in probability not to be as dramatic from 70 to 80 as would be the case if you're going up from 10 to 20. I think you get the point that I'm trying to make there, but that is an obvious weakness in the linear probability model. So to the rescue is the logistic regression model, or the Logit model, which is a nonlinear specification, unlike our guy, the linear probability model. So the cumulative distribution function of the Logit model is so expressed. This exp that you see here is actually the base of natural logarithms. It's the key. If I go here to your calculator, that's it right here. This guy right here, that's the base of natural logarithm, the exponential term that you see there. All right, so now unfortunately we cannot estimate the Logit model with the ordinary least squares, and so sorry, you can't use Excel. Excel is not yet equipped to implement that process. So we're going to use the method of maximum likelihood estimation found in virtually every econometric package like Minitab, SAS, SPSSX, Shazam, and my favorite, eViews. So let's look at a quick example right here. All right, so here a researcher is seeking to use the Logit model to estimate the choice that a student would go into the field of sciences given the student's GPA. So real quick, here's the regression model right here. So it's a two-variable model. And here y would take on the value of 1 if the student chooses a science field in college. And x1 is the student's high school GPA. So the hypothesis here is that the likelihood that you'll choose a science field increases as GPA rises. So these are the maximum likelihood estimates that have been produced, and as you can see here, the coefficient for GPA is a positive value 1.5448. And so we summarize that since the regression coefficient, which is repeated here, is positive, we can infer that GPA has a positive influence on the predicted probability of pursuing a science field. Now though, the exact impact based on the estimated coefficient value of 1.54 is not quite so obvious. For us to be able to interpret this in a way that's meaningful, in a way that highlights the changing impact of GPA on the likelihood that a student would choose a science field, we would need the estimated Logit model, which is this. So with this, right, we've plugged in all the estimates that you see right here. And what I did is to go on spreadsheet and I calculated what p hat would be for different GPAs. And as you can see here, surely as GPA rises, the likelihood that a student will choose the science field also increases. But quite so remarkably, the change in probabilities is not the same, it's not linear. So for example, the predicted probability increases by 0.18 as GPA rises from 3 to 3.5. You can see it right here. But it only rises by 0.13 right there when GPA increases from 3.5 to 4. And this concludes this presentation. I'm Pat Obi from the Purdue University campus in Hammond, Indiana.